Hello, everybody, and welcome back. I'm delighted to introduce this presentation from Thomas at Epishine. Thomas is going to give us a presentation on laminated photovoltaics for indoor applications. As always, we will be taking your questions after the presentation, so please do leave them in the sidebar. I'm now going to hand over to Thomas, and I will reappear at the end of his talk. Over to you, Thomas.
Super. Thank you, Chris. And thank you, everyone at TechBlick, the organizers. I'm very humbled to be here today among you all, my peers. And today we're going to talk about, just as Chris said, laminated photovoltaics for indoor applications. A theme I think there's quite a few other talks on later on, so hopefully we can build on each other. But before we get started, I would just like to report here from Linköping, Northern Europe, that winter is coming, so get yourselves all prepared. And then we get into the outline of our presentations. So the first thing I'll talk about is just my company, Epishine, what we do, where we are, where we come from, and also the concept of light energy harvesting, which is what we do, or rather what we make products for. Then I would like to talk to you about the technology that we have developed, why it ticks, why it works, what makes this good, and also very briefly on our industrial perspective on OPV, and particularly also the aspect of light energy harvesting. And finally, done some summary and take home. But first things first, Epishine, the company, we were founded in 2016, very recently, very young company. We started operations in 2017 even, I would say, so 4 years old or so in operations. We are rapidly growing, hovering around 30 employees currently. And we develop and manufacture and also sell light energy harvesting in the form of OPV again. And these are then particularly well suited for low light environments. Our dear grandfather of the company and co-founder, Ole Ingenes, is a professor here who's been doing a lot of research into organic electronics and specifically organic photovoltaics for a very long time. And we at Epishine, we solely focus on R2R processes, so roll to roll, very, very scalable and cheap in the end. So Epishine, we are currently residing in phase 1 to, I would say, 99%, and that is where we're gonna keep the talk today, powering Internet of Things. We all know the field, I think. We want little devices everywhere that measures various things, and all those little devices measuring things, they need a tiny bit of energy. And that is what we supply. Looking slightly into the future, we are also considering looking into what one of the previous talks was about, where traditional solar fails, facades and lightweight constructions, but we're not quite there yet and will probably not be for a few years. And finally, on the slightly longer term, maybe even the dream of us to be able to contribute to the mitigation of the effects of climate change and really roll out the large-scale solar cells, as the printing and coating and roll-to-roll technologies can produce very, very fast and a lot. One is allowed to dream for now. So first things first, again, with the current phase 1 IoT, why do we do it? Well, the driver of the issue is the issue with the batteries. The batteries themselves, driving these small units that collect data, again, they're not very expensive. The cost aspect comes in when you need to replace these ones. And you can also look in the center of my screen. There's a little quote about the take from a company on how that could look. So both the replacing of batteries is expensive, and the waste of batteries, quite a lot of mass, complicates things quite a lot. So we strive to provide an alternative solution, powering things with light. And we're looking to do this in a few different market segments. The 3 that we've currently identified and are working with various customers inside is the ones I encircle here. That is home automation, retail, and security. And I think the common denominator for all of these ones is not to completely circumvent batteries or to not use them, rather to prolong the battery lifetime so that it matches up to the product lifetime. It would be the same as the battery lifetime is the end goal. Another way that we add utility to the devices would be that you have a period at daytime when people are working, for instance, in an office. You have more light, and hence you're able to to send more data or use your device in a particular way to a higher degree than nighttime when you don't have lights. And finally, the case which we don't see so often, but have to some extent in the security segment scene, where we can completely remove batteries. And not many, but a few are interested in doing so, because that if the device doesn't have any lights, it is impossible to power up. And hence, it's very secure and safe when you want it to be off completely. And of course, when you want to operate in these let's put it like this. When you operate outside, it's very obvious where the light comes from. If you're in the northern hemisphere, you tilt your solar cells a little bit and you face them south, and you will get roughly the maximum amount of power possible. In the indoor space, roughly where I stand, there is the maximum amount of lights. However, usually, not always, but usually we want to put our devices a little bit, not quite invisible, but at least not in the center of view. And in those corners, in the corner case, there is less light. And you need to be able to fully function in these areas where there is less light. And this is quite tricky, it turns out. Usually the scaling downwards in light is tricky because of some issues that we'll be going into soonish. So we pride ourselves quite a bit here at Epishine that we'll be able to retain power all the way down to very, very low lux. Here in front of you see two graphs, one at 500 and one at 50 lux. Very, very little light. Probably where I'm standing right now is about 300 lux. So at 50 lux, there's very little light. And usually you see, as we do for some of our immediate competition here in amorphous silicon, the devices start to spread, simply because there is a varying degree of shunting in these devices, shunting or short circuiting, which I'll explain very soon. So reiterating the point that I made in my last slide, at the very, very low light, in these cases where we want to put things up in corners and so on, we need to operate at maximal efficiency in order to reliably power the devices that we're looking to power. So we are very fortunate to be able to do so now, because we just launched our product. It looks a little bit something like this in the real world, and you can see in front of you how it looks more conceptually. I will not get into the details exactly of what it can do and so on. You'll be able to find those things both on our website and also in our booth. I'm sure either of the organizers or even me myself can point you there if you can't find it for yourselves. And even more importantly, you can actually buy this one since some time now, both the modules themselves and the eval kits. The eval kit that we sell is then meant for any one of you to kind of rip up the batteries from your device and then try to power it with light instead of the batteries and see how that works. So please visit our booth or website for more information on that. And on to the next one, I would like to walk through a little bit on what makes the technology tick. And unfortunately, I have to start with a little bit of theory. I hope you can bear with me there. I think the case that most of you guys out there are familiar with, and I'll not go to the very deep details when it comes to IV curves and so on, is the case of the sun. We generate somewhere in the range of milliamps. And of course, when we increase the series resistance of the device, we get more and more losses. There's a lot of current passing, there's more resistance, we lose power. Not so nice. If we vary the parallel resistance instead, the resistor that goes in parallel with the generating element, we don't see much effect if we just vary it a little bit. Of course, if we vary it a lot, we'll see a loss at some point. In the case of the indoor or low lights, the situation changes. It's actually backwards. So since we generate so little current in where I'm standing right now, the little module I have here, we have very low currents in the microamp scale instead of the milliamp, and we can vary the series resistance quite a lot without causing any losses. However, if we vary the parallel resistance, which is another way of saying how shunted it is, we quite rapidly start to see big losses when the leakage current going through the device becomes in the same order as the photocurrent that we generate. And this, of course, causes big losses. And this, again, just to remind you what I talked before, is what happens in our competitor cells, although not in ours, because we can ensure that we have a very, very good power resistance. And why is that? I'll strive to explain the technology that we have developed here over the last few years. So if we consider the case that I'm sure you're all familiar with, where we sequentially deposit the solar cell on top of a flexible substrate. So we put down our front electrode, nothing strange. We put down some interlayer to make sure the current goes in the right direction. For the case of OPV, we put down very thin layers in the order of 100 nanometers or so, maybe slightly more, 200-300. It's quite easy for the active layer to have some defects in it. And either they are there from the beginning or they're caused by the position of the back electrode. And when that happens, we get shunts. This is the real physical mechanistic explanation for the parallel resistance. And this causes the leakage current that I just talked about in the slide before. What we at Epishine do instead is that even should we have these defects, we kind of create half a device on one side, on one substrate, and the other side, another substrate. We have the other, let's say the cathode and the anode, which we then laminate together in a hot lamination stage. And we will not have, even if the defects are here, we will not have any losses due to them because the electrodes never meet. And this is why we're able to uphold high performance even down to the very, very low lux numbers. The case here, going back to the product slide again, this one operates fairly well, even down to single-digit lux. This is a 10 lux. We can retain fill factors above 70%, which we're extremely happy with. And fill factor, of course, as I think you know, scales directly with the power. And this is the first thing you lose should you start to shunt your device. And why is this relevant, you might ask? At 10 lux, there's barely any power. Well, it turns out some of the people who do RF harvesting, radio frequency harvesting, they're used to extremely low amounts of power. So even if they get a couple of single-digit lux worth of power out of our device, they have a lot more to work with than they usually do. That's one of the cases of being able to augment the function of these devices. Going further, maybe you would ask, so we make it very differently. What about mechanical stability? Or maybe it's just my self-conscious speaking. Is it really mechanically stable? Yes, very much so, I would say. I think we have really, really good numbers here. We have 100% power retention upon 10,000 bending cycles, even at 1 centimeters of diameter. So we're very happy with that. And further, just a tiny bit more on the module, the spectral range covers very well indoor lighting. So you can expect high power in any LED, fluorescent, or similar type of lighting that you would see indoors. Finally, on the technology end, an important aspects. Here you see a collection of form factors that we would be able to do in our process. Some of them useful, some of them less so, but maybe a little bit interesting for your imagination. One interesting case is when certain customers look to retrofit our modules into their pre-existing chassis or device structures. Sometimes they need to accommodate things like a screw tower or something, which is exactly what happened in this case here. We worked together with a lock manufacturer, smart lock manufacturer, who needed to accommodate space again for these screw towers. And we are quite easily able to do so by just adapting the tooling, our process, the cutting and the coating. Yeah, it makes us able to do a lot of various things. And one more thing that I would like to point out, which is maybe not so obvious, is that we'd like to think of these ones as labels or stickers. And that will become more apparent when I start to talk about the process, which is my next section of the talk. So our view on the industrial processing of OPV meant for indoor use then again. So the first thing is that we'd always like to stay in ambient conditions. We, from the device point of view, it would be best, of course, to stay in vacuum or maybe in nitrogen, but it makes it a little bit trickier for the operator. There's trickier setup, trickier to control, trickier to do quality control. So we like to stay in ambient conditions where it's easy to modify things and change form factors, all those things. So making it easy and adaptable. If you're familiar with other types of solar cell materials, you would maybe be a little bit surprised that the processing temperatures are very, very low. We prefer to stay below 120 degrees. Absolutely maximum is 140 in our process, simply because we start to stretch the substrate quite a lot if we go above these temperatures, and that causes some detrimental effects downstream in the process. Also, an important aspect from the bottom up when we choose new materials for our stack, we don't want anything that we need to dry for a very long time. So a few minutes for each processing step is the absolute maximum that we accept, and hence keeping the throughput very high through the process. And this slide I will not have so much time for. It's my last slide, which is a little bit bigger, but I would love some questions on this one in the Q&A session, or maybe even in the talk afterwards. But going through it step by step, the first thing we do is that we pre-treat and we print, very straightforward, rotary screen printing, nothing strange. The technology has been around for many, many years. It's incredibly robust. We put down both graphical rayas that makes sure that we can be registered for the rest of the process, and also the bus bars and the contacts for our devices. After that, we coat our stack in multiple layers on top of each other, where, of course, that's the most complex part of the process, where we put by far the most R&D hours into it. So even if it's just one step here, it's in the center still. Yes. And then comes the reason I alluded to the label industry. We have a lot of overlap here in the standard processing steps, like it's lamination and die cutting, which we do in 2 steps. So in this case, the lamination actually creates our device, and then we go from a continuous way of processing into a discrete one, where we singulate our device onto a carrier. And also, as I alluded before, the material that we use is very sensitive to both oxygen and water. So hence we need to encapsulate it using a UV resin, which is also easily done on the roll in a sheet to roll fashion, after which we die cut yet again, and we have our finished product, which we can then contact and measure, integrate, and ready to go, essentially. So that concludes my talk, and I would like to leave you with the take-home message. The first one being that the indoor market for PV is taking off. We're getting more and more traction all the time from customers in various segments, new ones all the time. And OPV, especially in that it can deliver a very high price performance ratio as compared to competitors, amorphous silicon probably being the closest one, except for that. Second point is that lamination enables a very robust process where we can keep a very low degree of shunting in our devices, which is of course very beneficial for the end case, the use case, because we can again retain power. And Epishine, the Epishine process allows us to quite easily adapt form factors to be able to produce anything that you would like to integrate into your products. And with that, I thank you for your time and your attention. And I hand it back to Chris.
Thank you. Thank you so much, Thomas, for that really interesting presentation. As Thomas mentioned, please do leave any questions you may have in the sidebar. Thomas will also be in the lounge in the break after this presentation, and I've included a link to the lounge in the chat. But Thomas, in the meantime, I have a quick question for you. What do you think makes you stand out so much from the immediate competition?
Yeah, that's a very good question. I would say there's quite a bit of legacy in the field, and I think we approached the OPV and the technology from a different point of view. We decided quite at an early stage that we would go for the indoor market, and the process that we've created is entirely adapted to that. So I think there's a lot of benefit at designing from first principle for a specific market. That is what makes us stand out the most, I would say.
Great. Okay, and I've got a couple of questions here. How fast does your process run? What is the maximum width of your R2R machines?
So currently we're still very much in pilot production. So we are in coating limited to web width of 30 centimeters, 300. And what was the other part of the question?
What is the maximum width of your R2R machines?
Exactly, that's 30 centimeters, and then there was one more point.
Oh, how fast does your process run?
Depends on the process step. The coding again is the central point that runs by far the slowest. We run it currently at 2 meters per minute, which is very slow. At the current stage, we don't have any reason to run it faster. Should we decide to run it faster, we could, within a few months, turn up the speed by a few factors quite easily. It's just a matter of engineering. It's nothing intrinsic.
Okay, another question has come through. Does Epishine have their own production facilities, and what is the outlook for yearly production?
Yes, we do have our own production line right now, again in pilot scale. In terms of volumes, I mean, these ones, even at the very modest speeds that we have right now, we can produce several million a year of these. So we're very, very confident in our ability to produce.
Great. Okay, another question here. Do you face any issues related to alignment? And if yes, how do you solve it? And the second part, when you laminate two parts of the module together.
Yes, exactly. So alignment is key, of course. Crossweb is rather straightforward, I would say. That works very well if you plan your graphical layer ahead of time, so everything comes into place. So Crossweb is easy. Downweb is trickier. I alluded a little bit to that also when it came to the temperature ranges that we want to use. And you also have to plan out your process quite in detail in order to accommodate any stretchings of substrates and so on. So that one is way trickier and requires a lot of optimization time. But again, we're at the current stage, we're very confident there.
Okay, one more. Does one need special electronic drivers to manage the OPV? Ooh, sorry, I've just lost that one. Let me find it. To manage the OPV energy harvesters. Do you want me to read that again, Thomas?
Yeah, no, that's fine. I think there is a video in our booth where one of my colleagues goes through that one in detail very, very well. So I would point you there rather than to try to explain it myself. But the answer is yes, you do need. In most cases, in the very simple integration cases, you could go without any power management. But in most cases do require power management. If you are somewhere, if you want to operate optimally, that is. If you're okay with suboptimal operation, that's of course then you don't need it.
Brilliant. Okay, one more. What is the advantage of OPV over other PV technologies like C-SI, SIGs, perovskites, and indoor PV?
I think I touched upon it in our design philosophy. The process that we work with is very straightforward. First, we have a wet part of the process, and then it's dry. Everything is done in ambient. It's high throughput, nothing that really limits it. We don't need to go to vacuum. Those are the main advantages, I would say. And also, I think the guys, Heliotech also pointed to the same thing. There's nothing intrinsically in the material, in the elements that we use to assemble our device that is non-abundant or expensive. Everything can be made quite cheap.
Great. Well, a really nice set of questions there, Thomas. A great session. As we mentioned earlier, Thomas is now going to be in the networking lounge and we'll take your questions there. The link is in the chat section. And also don't forget our festive quiz. There may well be a festive image hidden on the Epishine booth. So do go and have a look. And we look forward to seeing you all in the lounge in a few moments. Thank you once again, Thomas. Thank you.
Thank you so much. See you soon.
See you soon. Bye.